Hello everyone, welcome to another session of Code with your friend, and I'm your friend. So, in the last session, which was a very ad hoc session, uh, what I try to do basically compare the performance of two solutions to the lead code problem. Let me quickly open the lead code problem here for you. So this was the lead code problem, which is the problem one, a very easy problem. The intention was not to solve this problem because you can find like hundreds of solutions to this problem on the internet. I think even LeetCode has like a number of solutions to that. The intention was to sort of use this problem and create two different kind of solutions. And we all know like the big O problems, at least people familiar with data structures algorithms, they know like the big O notations, why order n squared is worse than order n. And my intention of this problem was sort of solve this problem into two different kind of solutions and then compare their results. I did like a very hacky benchmarking kind of way. Let me also reiterate that just to refresh my own memory and also yours. Let me open my friend VS Code here. The particular code that we had written was this one, runner. I am mostly familiar with Java. I'm trying to learn C. I did some C when I was in college, but that was like long time ago. After that, I did mostly my professional development in Java or related object-oriented languages. And I want to learn more about C and I want to go more towards like system level understanding. So this series of videos is sort of my intention to clarify my own understanding and as well as share it with you if you get benefited as from that. Anyway, a lot of rant. So coming back to this, what basically I did is implemented two different classes. Let me see if I can navigate from here. Oh, awesome. I can actually. So one of them, LC1, it used a map implementation of that. And what it does, it basically just traverses the array one time. So just to reiterate, the problem was you have an array. Let me go to the problem there. You have an array, you have a target number, and you want to find out two elements within that array whose sum is equal to the target number. And what we needed to do is just return the indices of those two numbers. It's a quite simple problem, and as you probably would know, we would try to have like a linear time solution for that, and the key to that is like using a hash map or a dictionary. That's the intention I think we did here. I'm sure like there would be like smarter techniques to do that, but this is like a reasonably performant technique. And what it basically did is every time we try to iterate the list, uh, we would keep another hash map where we would know this is two number, right? So if number one is present, we want to check if the target minus the number one is also present there. So that would ensure that there are two numbers in this array whose sum is equal to the target. And that's what I think we are doing here. So let's say in this particular example, or whatever lead code had given here, in this particular example, 2, 7, 11, 15, the target is 9. So our solutions are like 2 and 7, which is like 0 and 1. So first time when we go into the hash map with 2, we won't find 7 there because we haven't encountered 7 yet. So what we would do is like we would just put 2 into that hash map. Okay, I have encountered 2 so far. Then next time when we find 7, at that time we would just find is 9 minus 7, 2 is there in that hash map and it would return true and we would end our search there. There is another way to approach this problem without using hash map. It's just like take one element, go to all of the elements in the list and see if there is a sum of this element and any other element in the list that would equal to the target. And that's like an order n square solution. So that was another approach which we had implemented called LC1 underscore 1, where we had these two for loops, iterated them, and did the similar kind of calculations. So this should ideally perform worse. That's, I think, fair. But my argument was there are more nuances to it, and some of these things we had discovered in our last program. We would obviously know like order n square is worse than order n, but there are few things what this big O notation actually means that gets proved through some performance analysis. So we can write some programs to analyze that, and through that we can understand why big O is important. We all know that it is important, but we should always question that, right? I mean, we should just accept it without like asking any kind of question. Let me try to put on one more light here, so I think it'll be not too bright, and maybe a warmer color. Yep, I think it's better. So, what did we do for benchmarking? Usually, industry standard benchmarking, there are tools available which where you will get like a very detailed analysis. Our benchmarking is like a very naive tooling aspect of that. Uh, what we did here, just put the mic. I think I am still audible. Yeah. So what we did here is basically instead of fixing our data set, we try to create test data on the fly. Uh, we also try to create a target data such that we can test the worst case scenario. And the way we did that was imagine the worst case scenario where you would hit a worst case scenario in this. In the worst case, what are we optimizing here in Bigo? We are optimizing the number of comparisons, right? Because essentially, like we want to reduce the number of times we reach this state. So if it happens like you have only the first two elements where you're finding like index 0 and index 1 and the sum of that, and if you have like a very large list, uh, that won't have like a very bad impact even if you are using an order n square solution. So the reason is like if you're unknowingly using a this solution and you're not seeing any performance degradation, there might be some reason like the input data is not actually has the property of extracting the worst case behavior of a algorithm. So the worst case behavior can only be extracted if you have the target data, which is the sum of the last two elements. In that particular case, we have to execute all the iterations, all the every time. I mean, we have to do that. So for if you have four elements and the third and fourth element has the sum is equal to 0. So you have to like for the first element you have to scan every entire list. For the second element you have to do that. For the third element you will be doing that, and at the last element you will be discovering that part. So it's like a lot of comparisons that we do. So while doing the benchmarking, we I think if you go through the previous video, we did discover that even I was not sort of aware of that. I just sort of tried to see the performance and then over time I discovered, and that's I think the fun of programming. But this is I think in a state. Let's actually run it, and we can sort of demonstrate the behavior. I will try to, so in this benchmarking, what I'm doing here is, so this I represents, let's actually call like, okay, so I represents basically the number of elements in the list. So we start with 10 elements, and as you can see in each iteration, we are increasing the number of elements, we're multiplying it by 10. So the next iteration will be 100, the next will be 1000, and so on. So what we're doing here, we are creating a test data set out of that. This test data set is also unique. Um, it takes a parameter bound here, but it does not use that. I mean, there is like a historical context why I did that. So we wanted to create like a random number set for that. But even a random number set, it does not exhibit that behavior what we wanted to extract. So we wanted to create a linearly sorted array with natural numbers. So we will just start with 0 and go to the end of the element and till the length of the array, and just fill it up with the next number, the next number, the next number, and so on. And eventually, the target we would decide as the last element and then the element before that. So those two elements, the sum of that will be our target. So in this particular case, we would ensure that there are. So the thing that we discovered is even if we use this rule for target and we had our test data completely random, there could be a case where coincidentally we create a list where we have like two elements which also sum equal sum to target because you can't enforce that, right? Like there won't be any such two elements. The only way you can enforce that is by ensuring that the list is unique, and then you have like the last two element sum. So that would be like the largest element and the second largest element, the sum of that. So no other element can possibly match that part. So in that way, we created the worst case behavior. We discovered like milliseconds actually doesn't reveal that much. So nanotime actually reveals us the computation time, at least in this particular scenario, better. When we try to create a million elements, then my PC hanged. So I'm limiting it to 100,000 this time. This benchmarking shows only for, I think, the optimized one. LC1 is the optimized one. So let's see what's the value that we are getting out of here. So what I'll try to do, I'll try to compile it once and then I'll run it. Oops. Nice. So here you can see for 10 elements, we are taking zero point 0.07 milliseconds. For 100 elements, it 0.44 milliseconds. For 1000, it's 0.5 to 0.38. It's actually increasing, but not that much. Now let's switch it with, okay, let's actually remove this details as well. Then we'll have only the benchmarking data. So we'll clear it out. Cool, beautiful. So it does like a lot of pretty printing as well. I am not sure why is it not ensuring like we have 6 elements here as well, but anyway, that's I think fine for now. So what would we do is like we'll just create this data set and I'll keep it for reference in my GDoc here. So this is like Java runtime for HashMap implementation. And once we go back, switch it with LC1 underscore 1, not using instance anymore. Compile it once again, run it. And now we start to see the slowness. This still completes, but I think if we added the million, then we won't even be able to complete. That's how bad it is. Paste it here and see the comparisons if you see side by side, right? Like whatever we are taking point. And the surprising thing is like even for the very low numbers, right? For very low numbers, this actually doesn't matter. So even till 100 elements. So even if you have a 100 element, right? And you have an order n square solution, the worst case performance is almost comparable with a HashMap solution. I mean, that's like a very, very big statement, but uh, that's also another thing that the intention is to understand from this is like big O notation is for worst case performance. Let's actually open the Wikipedia page for big O notation. Probably I also learned what it is. What is big O notation? So big O notation is a mathematical notation that describes the limiting behavior of a function when the argument tends toward a particular value or infinity. Big O is a member of a family of notations invented by Paul Bachman, Edward Landau, and others, collectively called Bachman-Landau notation or asymptotic notation. Letter O was chosen by Bachman to stand for order or the order of approximation. Anyway. Okay, yeah, sorry, I had to take a little break. Um, So yeah, coming back to I think the big O notation. So big O notation actually characterizes functions according to their growth rate, and different functions with the same asymptotic growth rate may be represented using the same O notation. The letter O is used because the growth rate of a function is also referred to as the order of the function. So that's why I think this is very important that big O is particularly useful for growth rate. So unless you have a problem where you basically encounter this growth rate, for example, in this case, obviously, I think even if you submit that to lead code, you will see that slowness. But in many scenarios, we might encounter cases where just trying to find like the most optimal solution might not make sense. So obviously, if we have the most optimal solution, that's better. But the most optimal solution will only be valuable if you have like a very large data set. And that's, I think, the intention of this. Anyway, coming back to today's discussion. So today I wanted to implement this solution in C because I don't know about C. So I want to write a HashMap based solution in C. So for that, I would turn to Google. Let's see what Google gives me. HashMap in C. Let's go to Stack Overflow, our reliable friend. Um, let's see. Okay, this is like a good upvoted answer. You know the basics behind them, it shouldn't be too hard. Generally, you create an array called buckets. Yeah, so I think the main story is Java provides us a library function uh, for HashMap. But C does not have a HashMap functionality, the data structure. So we have to create that data structure ourselves, or we use some library implementation. It's generally better not to use library for personal programming because then when do you learn? For when obviously for your work or for anything professional, rely on libraries. At least the reliable libraries. Don't rely on all the libraries because there are like too many libraries out there. Just compare that, evaluate which one works better for you, take that out. If there is no solution exists, possibly then write yourself. But while doing personal projects, just take the other approach. Start implementing yourself. Try to code as much as possible yourself and then look at the libraries, see implementation, how they're doing. I think that's my intention here. But even to do that, I need to look at because I'm not sure even how to do that. So I'll try to get inspired from some of these solutions. So let's see how they're doing there. So what here this guy is saying is like generally you create an array called buckets and that contain the key and value with an optional pointer to create a linked list, of course. So why do we need that? Because if we have hash collisions, then we'll still need to uh, store that element in the same bucket. So we need a like a pointer. So basically we need like an array of linked lists. And when you access the hash table with a key, you process the key with a custom hash function, which will return an integer. You then take the modulus of that result, and that is the location of your array index or bucket. Then you check the unhashed key with the stored key, and if it matches, then you found the right place. Otherwise, you have had a collision and must crawl through the linked list and compare keys until you match. Note some implementation use a binary tree instead of a linked list for collision. I think that, like that's obviously like quite advanced. We are not at that level. There's like a fast hash table implementation, but I won't look at that right now. This is, I think, good enough information. I think I know how an array works in C, I guess, and possibly how to write a linked list in C. If I can combine them together and write a hash function, then I can create a hash map implementation. So let's try to get coding here. So let me okay, I think this phase code, we won't need that because we won't be in the Java directory anymore. So we'll go to the C directory and yeah, let's open code here. So we will create a new function 1_1. We'll treat the same problem name. The first, what we'll do is we'll implement a hash function. And how would we implement a hash function? So for that, what I would do is I would look at how the implementation of Java's hash code is, and I would just try to copy that here. Java hash code implementation. I prefer to look only for Stack Overflow because that usually points to better solutions. Good implementation is Josh blocks. Yep. The best thing to hash value. For every field f tested in equals method, calculate a hash code by C. If this field is a boolean, do this. If the field f is a integer. So in our case, we want to just find an integer, right? So basically what we can do is, so we can just choose two prime numbers and multiply the number with one prime number, add another prime number to it. Then we do modulo with another prime number. Let's see how good a hash function that we end up with. Let's see. I mean, I don't know. I'm just trying things out here. So I guess it would also depend of what my capacity of the hash table is. If I have a hash code of a number, let's say I multiply a number with 37 and add another prime to it, 43, and then what is the largest prime within 100? That's largest prime within 100 would be 97, right? Is 97 a prime? I think so. Largest prime less than 100. A lot of people have asked that. Phew, yeah, 97 is a prime. So then we would end up with this number, but the problem is I think it's not right. What we can do is probably we can swap these numbers. I think let's make it like this. So we'll end up with some hash function. So I think we will see like how good a hash function this is, but we can come up with another hash function there itself. So this is, let's say this will return my hash code here. So if I quickly test that, so for let's say for first 100 numbers, or actually I'm trying to do a modulo, this should be modulo 37. So ideally it should be less than 30 or something, just for a small number scenario. I will try to do a printf of hash code of I. And let's, okay, no, I think I can run it from command line also. gcc -o1 okay, and then I can do one this. Because okay. Or I can do some very C specific things like which I don't like, but I think they should work. I mean, not here, this is not right, but here, post increment. This is ideally a very anti-pattern to do, but in your personal time, you can try out all anti-patterns. Interesting. Looks quite random, uh, but obviously there would be some collision. We can come back to that later. Um, anyway, so going back, what we need to also implement is a linked list, and we also want to have an array of that linked list. So every time we find that, we just create. So for linked list, we need to define a node. So I think this is one approach. Type div struct node. So I have integer value. I forgot the linked list. And this is how bad I am in C. I have to look up like linked list implementation. God. But I mean, there is nothing to be ashamed of. You always learn. So yeah, I don't need that. Yeah, I don't want to keep calling struct node struct node. I think I mean the struct node part I get it, but the only thing I need is the type diff thing. Okay, yeah, this is basically exactly what I'm looking for. Struct node, integer. Yeah, just call it value. I think it's easier for me. Then we have a node t. So this is I have defined a node. Now what I need is I need to define also an array of that node. So let's say I have, okay, so this node t type. This is my map of 30 characters. Initially, I think it will be all empty, but I have to first, it depends. I mean, I don't have to initialize it. I think initially they will be all empty, right? Will they be if map I is not equal to null, then printf what? Why am I having trouble here? Expression must have arithmetic pointer but has type. Can't I define something like that? Array of linked list in C. There is no point wasting time here. So anyway, we're going to wrap it up within 1 hour. So just arrays of linked list. Yeah, something exactly like that. How do I create that? Okay, yeah, I think let's just call it node. I think that's just easier to do it. Not node shape, not the node, and node pointer. Yeah, my bad. Node pointer, and then we have a map of 30. Now I think it's this one, right? So then we can possibly let's actually take this one to the right. It's easier to compile it here side by side. I also don't want to. It's visible. Yep. I think the only problem is it might impact. I have to take myself. Yeah, I have grounded myself. So now it should be fine. So let's just do the of that. It is not null actually. So we have to initialize with null. What happens if I just do something like this? Can I do something like this and see? And compiled. Only the last element? Or what? I mean, the rest of them are all null. Okay, so I think 30. Yeah, let me actually do something here. Let me download copyright free images. I recently learned a technique. Images of penguin. Yeah. So yeah, this penguin I think looks cute. I will just download this guy. Save image in the desktop. What I'll do is basically I would just take this guy. Where did this guy go? And bring this guy sort of open it. Let's say I want to open with paint is fine. What I am trying to do here, just a second, it'll be evident. So what I am trying to do here. Can't resize the window beyond a certain. So I can just create maybe a Firefox window, something like that. I can make it arbitrarily smaller, right? Yep, I can. I don't need all of this. So big problem is I want to create something blocker for my screen where my camera is applied so that I'm aware whenever I'm coding, but I still want to have that thing there anyway. The other option I have is like make my coding window a little bit minimized. I think that's also another better solution so that I don't overlap with that. So I always have some gap here. That's I think better because I don't want my camera to sort of interfere with the coding space. It's fine. Keep it like this. I think vertical space I can ignore. Some of the horizontal space I can use. Yep. Fantastic. Okay, it works. Yeah, for I think 30, this is the case because oh yeah, this is happening because of that post increment part. Now I think we are cool. So we have a non-initialized map of array of linked lists. Now what we need to do is we have to Uh, Basically, what does a hash map has? A hash map has a put and a get operation. And we can also do something complex, but for our purpose, we just need put and get. And how can we put and get within the hash map? Let's see if I have the hash map outside of this context. Then also I can still access that. I want to implement a put function on top of it. So basically what I want to do is whenever I find a hash value, um, that hash value needs to be mapped to this. So this hash map needs to be till value 37 or 30, whatever is there. The only thing is I should do a modular like that, or it could be 100, or we can have a hash define of a constant C, my C knowledge, where it shows it contains hash capacity 100, and then we use that everywhere. Whenever we change it, everything changes. So something like this. So what we do here is everything will map to something less than 100, and that should be fine because my hash capacity is there. And by put function, so what the put function would return, would it return anything? No. It will just should put a value there. So if I have a value, what it needs to do is first it needs to check what's the hash value of that is. So what I'll do is I'll create a hash code of that value, and then I'll check if map hash is, let's say it might be pessimistic. If it's null, then what I do is I have to create a map hash. So what I need to do here, I have to do a malloc here. So malloc, although I think the linked list implementation should have that, right? This kind of thing, yeah. So what I need to do here, I need to create like a malloc size of 9, yeah, this. So I need to allocate some memory, and in order to do that, I need the stdlib function. I know that stdlib contains some of the memory utilities, right? So we can do malloc now, and size of node, and then basically this map of hash, this value will be my value, and next will be null. Otherwise we will find we have to define like a current node, take a reference to that. What's the error here? Oh yeah, it should be a no pointer. So while current dot next is not equal to null, current is equal to current next, right? And as I think we have discovered, like current next is null, so in current next we'll do a malloc, and there we will get that size of node, and current next value will be this value, and that should be it. So let's see if I try to do that. Put I. Will it throw some kind of error? So I think after a certain point, so this means for the first few values when we are inserting, we are encountering nulls, and then we started encountering not nulls, right? What it can return possibly is, just for our testing purpose, an integer of the index. So if it's like a first point it's inserting, then it can return a 0, or it can keep like an index of it, and every time we are iterating we can return it. The only catch here is it'll be either, I think it should start from 1, because what will happen is even if you have just one element, at that time you have current next is null, so you won't go there, so current next will allocate that. So that's like the first element that you're allocating. So then it should be like return I. So, but I have to print it somewhere, right? Printf put %d fine. So then now interesting. So I think we need to just have \n, a little bit problematic. So I think put is not working as expected, because let's say for this, right? So whenever we are encountering this a hash code, we are, let's call this hash code of is person D. I think this I is also not doing right, so I plus plus. That's why this post increment is very bad, because it just messes up with your code logic. Do I need to check this? I think this is not necessary now. So put should not return 0 every time. Should not. So hash code of 0 is 43. So if we encounter like the hash code of some value, so what we need to check here is hash code. I think it's a deterministic function, so every time we call it, it'll return just 1. So we can just keep it here. Integer hash is equal to hash code of I, and hash is, I think, some yeah, I mean we can do more printing here, I guess. So we again calculate hash code here, which is needed. Then we map of hash is equal to null, then map of hash is equal to this, and then return 0. Um, let's see. Map or map percent d is null. And this will be my hash key. There is null. So it is always coming as null, which means is like the initialization is not happening properly. There is some garbage which we are doing here, some problematic thing which we are doing here, which is creating this issue. So definitely we are finding some hash code collision. That's for sure. So for example, hash code of 0 is 43, 1 is 40, 37, 34. So let's actually do this thing. After we come out of this scope, um, this should not be null, right? Which is, I guess that's what's happening here. Um, Map of hash code. I'm calling hash code number of lines. It's not a very expensive function, so it's fine. Anyway, it's just for testing. Okay. If I comment this one out, comment this one out. What does this put? So basically in this, .43. Is it like we are creating the perfect hash function? I don't think that's happening. I don't think that's happening. I guess the better way to check this is reducing the capacity. Then I can probably uh, check it manually. So we have 30741. Oh, this is interesting. if we just did like number percent hash capacity, then also it would got it, got it, got it. So I think our code is not wrong yet. At least it has not been identified yet. But if we have like twice of hash capacity, um, then what? So now put is all one, right? And then if we have like this, so because okay, okay, I think I'm sort of getting at it, but let me just clarify it one more time. Yeah, yeah. So this is so very dumb of me. So what essentially is happening here is the hashing function, that the way we are testing this hashing function, it's not a real world scenario. So what we are doing here, we have this linear set of numbers, natural numbers, and then we are just putting them into the hash. So what would happen with this fixed set of deterministic function? They are all falling into different buckets. So even if this function looks random, what it randomizes is essentially like the order between natural set of numbers, but they still remain the natural numbers. If we have, let's say, I mean, a random stream of numbers of hash capacity, which is multiplied by 10, and then even within that, I think even if we within the same hash capacity, if we have just the random number instead of that, then probably we should see some conflicts because we can see like the same number coming in and if the same number comes in, probably I think that's still fine. But if we have let's say very small hash space and then a very large number space which is mapping to that, then this problem might happen. But according to I think this, we are still sort of able to find it and we are able to resolve it. So I think this hash function sort of works right now. Um, let's see though. Once I have the get function, I would have more confidence. I think I'm probably like having a lot of dumb comments here. If you're watching and if you're finding something dumb in my comment section, then let me know. If you find something dumb in my comments, then let me know in the comment section. So what? Okay, so essentially, so this is basically. Hold on. What the f am I doing? I'm creating a hash map, right? So where is the key and where is the value here? The key. So the key, you're finding a hash for that and then so it should be a key value there, right? So what is my key here? So I should hash my key and based on the hash, I should put my value there. And then I should get, just pass the key, calculate the hash, and just find. So in this particular case, what I would find is node pointer. So I have a key and then I find a hash, then I'll probably find possible value with it. So I'll need the map node, that'll be map of hash and so what I need to do is, if it's a single node then it's fine, or while map node is null, I need to check if map node value is equal to key, is it? I need to have the key there also, right? Because multiple key can map to same table. So the key also needs to be here. Yeah, what the... So the key needs to also be here. See, these are the things that you discover. So you also need to keep the key, right? So map key is equal to key, and similarly, when I come here, I need to also keep the key here. Current printers yet can be removed, and then I think we're almost at the 1 hour mark. So I'll maybe give 5 more minutes, then I'll sort of wrap up. And if needed, we'll probably skip over to the next video. Spill over to the next video. Node value, value is key. No, key is equals to key. Then we'll just return map node value, and we'll just iterate map node. And I think there should be some return value of it. We can always return key here. Ideally, we should not reach here. Implies, so ideally it should be -1 or some negative value. Implies the map doesn't contain the key. So we can have like a similar contains key function, something like that. But yeah, if get returns any non-negative number, then probably the value exists. So which implies like the value cannot be negative, which is I think also a wrong thing. But for now, it's fine. Only for hash map of positive keys to positive values. Okay, so what we can do here, we can probably just do something similar to this. So for each capacity, we can, now I think we don't need that. So what we want to do here is we can put some random number. We can put, let's say, 15, 20, and let's see if I'm able to recover that. That would be a good result. Get 15, right? Yep, so we are able to recover that. That's, I think, fine, but still there are a lot of edge cases which we haven't covered yet. We have to test it more. We have to plug this entire solution to the two-sum problem. Probably like we are doing verbose code, we have to reduce the load code a lot. We will see some other implementation, K-hash and all. But I think this is sort of a good learning. What do you think? Let me know. See you in the next session. Bye-bye.